let me introduce our last speaker, Dr. Dongsoo Lee. He is an executive officer at NAVER CLOVA. Before joining NAVER, Dr. Lee was with IBM T.J. Watson Research Center and Samsung Research. His current research interests are DNN model compression and DNN accelerator design. Today, he's going to talk about extremely low bit quantization for transformers. Dr. Lee, please.
Thanks a lot for the kind introduction. I'm very honored to be invited. Today, I want to share our experience of quantizing transformers using only a few bits to represent weights. And then I will also present our efforts to develop a dedicated computational kernel to gain some benefits of extremely low bit quantization. As a result, we can make the inference of transformers much faster while we have significantly reduced the footprint. So the reason why we can achieve an extremely high compression ratio for transformers is basically because DNNs turn out to be extremely redundant. So redundancy is basically very useful to expedite the model training process because over parameterization can give us a reasonably good local minimum quickly. Especially in 2019, researchers found that if it is possible to obtain a sparse network called the winning ticket of a good initialization, then our training can achieve better accuracy with a smaller number of iterations. Because it is difficult to find such a winning ticket in the very beginning, what we are doing usually is to try a combined form of numerous kinds of sparse networks with different initialized weights. As a result, after training process, a lot of weights become redundant, and removing those unnecessary weights does not degrade the model accuracy a lot. There are a lot of similar stories of redundant parameters. For example, on the left side in this slide, there is a reference model, say resonant 34. Now we increase the model size to obtain a larger model, to say a wide resonant 50 model. Now, even though we do not perform training, it turns out that there exists a subnetwork with a high sparsity that can achieve the accuracy of a trained resonant 34 model. So this means that for a randomly initialized wide resonant 50 model, there is a subnetwork even from the very beginning without training that can give us a reasonable model accuracy. So as a result, throughout numerous publications, we now know that if it is possible to estimate a good subnetwork, then training can be a lot simpler because we can remove a lot of redundant computations. But practically speaking, the lesson is that a normal model training process induces a high chance to reduce the model size greatly. So particularly in this talk, we are interested in utilizing such high redundancy to reduce the number of bits to represent a model. So let me talk about computing system design for efficient AI inference. Even though we can come up with a lot of compression techniques such as pruning, quantization, and so on, in order to utilize high redundancy, such efforts need to be combined with the hardware design and software design in kernels and various libraries. So that means without a holistic approach, integrating many stacks of a system, it would be quite challenging to see benefits of model compression ideas. So in this talk, I will introduce not only a quantization method dedicated to transformers, but also a novel matrix multiplication kernels to support such quantization efforts. And then we will see how much practical gains can be obtained in a mobile system. So in this slide, we see an original architecture of the transformer design to support neural machine translation. So it mainly consists of embedding matrices, encoders, and decoders. So in general, embedding matrices are shared not only to reduce the memory footprint, but also to improve the model accuracy, considering the different number of updates for tokens in a vocabulary. So even with such a sharing technique, we can observe that the size of embedding is significant because of a large size of vocabulary. Another interesting point is that the decoder is auto-regressive. So therefore, latency is usually dominated by decoders. So now let's discuss how to quantize transformers efficiently. So one of the well-known quantization methods would be uniform quantization. we set a particular range for values to represent weights, while a range is evenly divided. Then each weight is mapped into one of discrete values. For uniform quantization, it is very important to find a proper maximum or minimum value, which is basically a threshold. If we allow a large maximum value, then we can represent a wider range of weights. But the resolution is sacrificed for a given quantization bits. On the other hand, if we have too small maximum value, then we may need to clip too many weights. And for uniform quantization, such a maximum value and resolution can be converted into a scaling factor and 0 point. So the major strength is in uniform quantization is that we can heavily rely on integer arithmetic units, such that hardware design can be a lot simpler. In fact, there are various forms of uniform quantization scheme. So for example, a scaling factor can be set for each layer or each channel. Another factor to consider is whether we allow different magnitude for the maximum value and the minimum value. So if two values are different, then we have a asymmetric format that needs additional computational complexity, even though the model accuracy can be slightly improved. In addition, we also need to consider where and how to apply uniform quantization for various model parameters. int8 is a popular choice for uniform quantization in general. So let me discuss some limits on it. So first, to enable int8 arithmetic operations, activations need to be quantized as well. Then the decision where we need to perform activation quantization is an important process. So in other words, we basically need to modify an original model to insert conversion steps or on-the-fly quantization steps. Moreover, since there are numerous highly nonlinear operations such as softmax and normalization, such as online quantization and dequantization are required. Then why still we choose int8 method as a popular one at the cost of such additional model design modifications? It is because of a high energy efficiency of int8 adders and multipliers as shown in the table. So what would happen when we apply int8, which has been widely used for CNNs to transformers as well? Is it still useful? So that is our question. So on the left side, in this figure, we see a structure designed to reduce our option memory footprint only, and all weights are immediately dequantized. In the middle, only matrix multiplications are implemented by int8, but unfortunately, recent efforts tell us that frequent quantization and dequantization demand large overhead in latency. So on the right side, some researchers suggested an integer-based softmax computation method to allow end-to-end integer operations. But even in this work, we have two problems. First, such integer-based softmax needs int32 multipliers that are actually very big, almost similar to 32-bit floating point multiplier. Second, 4x memory reduction and speedup would be the upper bound. To overcome such challenges, we adopt binary coding quantization scheme, or BCQ in short, which is basically a non-uniform quantization method. So suppose that we have k bits for BCQ, then there are k number of scaling factors which are real numbers and can be shared by weights in a row or layer. And then each weight is now represented as addition of k scaling factors, while the sign of each scaling factor can be flipped depending on the binary values represented as a vector b, so in this equation. So as a result, each weight can be mapped into one of 2 to the power of k real numbers. So it is known that since the expected value after quantization remains to be the same as an original one, so as such, even 2 or 3 bits are usually from Eric. So again,
Can you mute?
Yeah, 2 or 3 bits are usually okay to keep a reasonable model accuracy. So in other words, BCQ or other non-linear quantization methods present a high compression ratio. higher than int A in general. But the problem is that such a nonlinear quantization requires special hardware or library designs. So that is our motivation to design a BCQ dedicated computation kernel called BigGem in this word to allow efficient computations while weights are still to be quantized. So one interesting thing for BCQ is that when weights are represented in the form of BCQ, computations can be a lot simpler. So let me be more specific in the next slide. So suppose that a weight is quantized by BCQ such that weight matrix can be converted into a set of scaling factors and binary matrices. So in this example, we assume 3B quantization for weights, while activations remain to be floating number of full precision. So we do not quantize activations, which are usually costly. Then X is multiplied into each set of scaling factors and the binary matrix 3 times if we have 3B quantization. So actually, we don't have to perform matrix multiplication 3 times individually. So we can concatenate 3 binary matrices in a vertical way, like this, to minimize the number of function calls. So now what happens is that we have almost no multiplications except for a few scaling factors because a binary matrix just affects each sign of activation value of S. So overall, BCQ enables a unique computation forms, and the fact that the expensive multiplications are not necessary is a big plus for us. However, such a knife format has a few critical problems. The most critical one is that we need a bit-level memory accesses to read the binary matrices. So even though we can transfer binary matrices in a bi-level to off-chip memories, computations cannot be performed in a bi-level. So for each activation value in X, we need a read each bit of binary matrices to determine a proper sign of an activation value. So one of the possible solutions to support such a bit-level, okay. So one of the possible solutions to support such a bit-level memory access is to design FPGAs or ASICs. But in this talk, as a cost-effective solution, we target CPUs or GPUs that have been already commercialized in the market. We can expect that for CPUs or GPUs, such a bit-level accesses will be quite slow. That is why we propose a new matrix multiplication engine based on lookup tables that can efficiently utilize CPUs and GPUs to run BCQ-based transformer models. Our work is based on the observation that a lot of computations are actually redundant when BCQ is adopted. So for example, in this figure here, when we perform a dot product for each row, many computations are duplicated. So for example, for 0.03 and minus 0.17 in this rectangular box in X, the same binary values are multiplied and more such a redundant computation will appear as we have a larger number of rows in a binary matrix. That usually happens as a model is scaled. Then, because of possible computations using activations are quite limited, we can pre-compute to all possible computations and store them in a lookup table. So the first step is to build a lookup table whose size is determined by how many bits of a binary matrix you used as an index. If you look ahead using 2 bits, then a lookup table has 4 entries and all 4 possible computations are performed in advance. Then a part of a binary matrix becomes an index to access a lookup table. So even though the size of lookup table is controlled by a few trade-off factors, but in general, 256 entries are generally preferred to optimize the performance. So from our technique, we have 2 positive effects. First, if we have a large number of rows in a weight matrix, then completing a lookup table method demands a smaller number of computations. Second, now we can access the binary matrices in bi-level. So we investigated those two positive effects using random matrices of various batch size and metric size. So we tried both PC processor and mobile processor in this experiment. So for BCQ, we assume 1-bit, 2-bit, and 3-bit quantization. And then for conventional method, floating point matrix multiplications are implemented by Eigen library or MKR by Intel, while we also try well-known libraries for INT-A computations. First, the thing to notice is that the BigGem is especially fast for small batch size, which cannot fully utilize highly parallelized arithmetic units in conventional engines. But even for large batch size, BigGem presents a good speed up because parallelism is not destroyed by BigGem significantly. So even though it is not described in this figure, naive implementation of BCQ using on-the-fly dequantization or bit-level accesses, actually BCQ computations can be even slower than conventional methods, even though memory footprint can be saved a lot. So now we have a computational engine for BCQ. So let me discuss how BCQ can be applied to transformers efficiently. So if we look into the structure of transformers, three major building blocks, namely encoder, decoder, and embedding matrix, present. Sorry, I don't know what's going on. Present a similar size. But the impact of each block after model compression would be vastly different. For example, embedding matrix for inputs is a simple lookup table, while a decoder is quite slow because of auto-regressive property. Because decoders and embedding layers are frequently accessed, we can guess cache is useful, and memory reduction can enhance cache utilization. So overall, to exploit such different characteristics, we propose a mixed precision quantization strategy to support three different building blocks using under 3 bits with negligible accuracy degradation. That is our goal. So let's quantize embedding layers first. So interesting feature for embedding is that each word or token in a vocabulary has a greatly different frequency in a data set. So what previously achieved was to group tokens following a range of frequency in a data set and to apply a low rank approximation to each group. But in our work, we follow a grouping as well, but each group is quantized with a different number of bits. So for example, tokens of high frequency are considered to be important and 4 bits can be assigned to them. While a token of a low frequency is assigned with 1 bit only. Such a quantization is useful for table or lookup process because we don't have to reconstruct each group as in the case of low rank approximation. So the implementation can be very fast compared to low rank approximation if we adopt a quantization. So in this figure, we first quantize the entire embedding layer using 1 bit or 2 bits. Then here 1 bit and 2 bit. Then we try a different mixed precision quantization considering relatively different frequency of tokens. So as we can observe in this table here, mixed precision quantization can obtain similar model accuracy of a 2-bit quantization. Then we performed a slight amount of retraining for the table here. And it turns out even with 1.3-bit quantization, it leads to reasonably good model accuracy. So compared to the baseline of a full precision, embedding layers can be reduced by almost 25 times.
So here's a quick, interesting question from the audience. So will this approach, BigGem approach, also works on CNN and RNN other neural nets?
Sure, yeah. Actually, BCQ has been widely introduced in the literature. So we have numerous papers for CNNs as well. So this idea has been published for RNN first because for CNN, relatively good research results are already there, but it's quite challenging to run transformer-like models with high complexity with a low bit quantization. So usually this kind of BCQ is considered for those large and complex models. But for CNN, that's totally fine. 2-bit would guarantee like almost full accuracy in the recent papers.
All right, thank you.
Okay. So for encoder and decoder, we investigated the sensitivity of sublayers with respect to the number of quantization bits. So we monitor relative sensitivity of sublayers by measuring blue score after quantization without retraining. Then we assign relatively different quantization bits based on such sensitivity information. So in this table, what we can see is that the feed-forward layer in this encoder and especially the cross-attention layer in the decoder are quite sensitive. So we have to pay more attention to those sublayers, and we may need to assign more quantization bits for those sublayers. Retraining algorithm is particularly crucial to obtaining good model accuracy. So even though we do not present specifics of our retraining method here now today, we adopted a non-regularization period as a way to control regularization strengths, and the corresponding reference paper is shown below in the bottom. We went through three retraining steps in order to run a gradual quantization process. So we first quantize and retrain embedding layers, and then decoder, and then encoder, following the relative different amount of retraining steps. So embedding layer is going to go through the longest retraining step from this plan. And this table shows our overall quantization results. So we have model accuracy of full precision and fixed 3-bit quantization and fixed 2-bit quantization first in the first 3 rows. Then we gradually quantize each block like this. And we compare blue scores for each case. So it turns out that our mixed precision strategy produced 2.6 bits per weight on average, while the blue score becomes even higher than that of fixed 3-bit quantization. So it is possible to realize 11.8x compression ratio without noticeable accuracy degradation, which is quite impressive. So let's discuss latency improvements when a mobile processor is selected as described in this slide. We have a Galaxy mobile phone. First, quantizing embedding layer only can reduce latency by more than 200 milliseconds. And quantizing decoder is also quite useful to reduce the latency. But quantizing encoder layer is not very effective compared to decoder or encoder. That means actually the autoregressive property is quite important and almost deterministic to give us the latency. So that is why we decided to perform encoder quantization as the last step with the least efforts. So even in the profiling of full precision, we see that the latency and flop have different stories, such that our strategy is correctly targeted for transformers. So on the right side, it shows that under 8-bit quantization has been quite challenging, and non-uniform quantization is essential, basically, for complex models like transformers. So this slide describes a specific example of translation to show the quality after quantization, and we can see that even 1-bit quantization for tokens in embedding can successfully maintain the overall translation quality. So that's in for my presentation, and thank you very much for your attention. Any questions?
All right. Yeah, thank you for your great presentation. Do you have any questions? So since we are kind of behind the schedule, let me have a just quick question. So if you actually make this algorithm, very nice quantization algorithm to hardware, how many performance boosts do you expect from it?
Your question is, suppose we design a dedicated hardware for this?
Yeah, something like that. Yeah.
I don't know. I think this is kind of an opening a new research area where the computation format can be totally different compared to conventional floating point or integer-based arithmetic units. So I don't know. Actually, we are working on it, and so the point is how we fully utilize all those interesting features from BCQ. It may have a long way to go.
Okay. Yeah, but considering it has really small footprint, I think we can actually fit it and accelerate the algorithm very much. Okay, thank you for your talk.
We especially want to give thanks to our strategic partners, which really helped us that we can make that event possible. So we have first our executive sponsors. We have ARM, which is the software and hardware foundation for tinyML. Then Edge Impulse, tinyML for all developers. Qualcomm AI Research, advancing AI research to make efficient AI ubiquitous. Sentient, end-to-end deep learning solutions for tinyML and Edge AI. And our platinum sponsors, Reality AI. They add advanced sensing to your product with Edge AI, tinyML. Then also we have Renesas, broad and scalable edge computing portfolio. Our gold sponsors, Latent AI, adaptive AI for the intelligent edge. Maxim Integrated, enabling edge intelligence. Seed Studio, the IoT hardware enabler. SensiML builds smart IoT sensor devices from data. SynSense, building sensing and inference hardware for ultra-low power embedded mobile and edge devices. And our silver sponsors, we have Aeon Devices, Deep Light, EMSA, Green Waves, Gravity Inc., HOTG, ImageMob, Geekzo, Rixon Technology, and SAP. So we really want to thank all of our strategic sponsors who will help us. And I hope you all enjoyed it and that we see you again tomorrow. Good evening, everyone.